Let's take a look at some examples where we're going to find the electrostatic potential. I want to just go over again the form of the electrostatic potential for a charge distribution, and you recall if you took a volume charge density ρ, we could determine the potential at a position r. We can take ρ being inside or outside and contained. We'll pretend that the vector r, the field point, is outside. So what we mean is that we have some volume which has a, let's call it tau prime, which has little elements of volume d tau prime, and those are positioned at r prime with respect to the origin. Our field point is at the vector r, and the important vector, of course, is the vector that takes us from the little charge element to the point in question. If this were the only charge that was available or present, then we'd get a E field that is parallel to r minus r prime. Of course, when we integrate all over it, the total will potentially change from along this particular direction. Well, if we take our volume d tau prime and we have this ρ, which can be a function of position, that's why we write it as r prime for the argument. The little charge within this volume element is just taking the charge density at that position times the volume element d tau prime. So if we take Coulomb's law in order to derive this potential, we did before, for a point charge we get k times the charge divided by the distance from the charge. If the charge were at the origin, then let's say a point charge, then out here at vector r we would have k, q, if this were q, divided by this distance here. And note that it's a scalar. So if we put in for our dq prime our charge density times the volume, we get this. What I was just pointing out is we're generalizing this equation here for a point charge. Once we have dv, we can integrate, and so we're integrating both sides, and so this side gives us v of r, and this side here gives us the integral, and this will be over the volume k rho d tau prime divided by the distance r minus r prime. And I just wanted to remind you that you can extend these kinds of arguments from the volume to the surface to the line charge, and so they just take on the form of these three equations, and you'll notice that a surface charge density times the surface area and a line charge density times the length gives us the differentials of the charge. Here's a nice problem. We have a line charge which goes from 0 to L, and it's a constant charge density. We're to find the potential for points along the x-axis starting at L on out. So we start right where we were talking about. In this case, we're going to use this form for the potential. The reason that I'm doing this simple problem is I want to identify the various elements that are in the integral. So here's our definitions. Here's the end of the charge density. Lambda is the charge density over that line of charge. And we pick a little element of length. This would be our dl prime, and we'll call that dx prime because it's along the x-axis. The vector that defines the position of dx prime is the vector x prime times x hat, and that's what we call r prime in this equation right here. The vector r is the vector, this blue vector, that goes all the way from the origin to the point P, which is at the position x. R vector is equal to x times x hat. The dq for a constant lambda is just lambda dx prime. So we can put our r and r prime into the vector r minus r prime, so here's what we get. And we can factor out the arguments so that we have the distance between the charge element and the point in question times x hat. Now what we do is just simply add all these up, and that's what we mean by integrating. If we look up here, now we have k lambda. Lambda is a constant, so we can bring it outside. Yeah, I didn't point out that the length of this line is just x minus x prime. Putting that in, then we'll have dx prime divided by x minus x prime. That gives us a very simple result. Here's the integral right here, and here's the answer. This is the answer for the potential. This is v of x. It holds for x L to values greater than L. So if you put in L equal to 1, then you can see that it's starting at 1 and going out to further x, and that it falls very rapidly. That's the potential as a function of distance along the x-axis. If we then look at the E field, we want to find the E field along the x-axis. We're fortunate in that the only component is the x component. So in other words, the y and z components are 0 because of the symmetry. So in other words, if the charge is here and you're going along this axis, along that axis you only have x components. You can differentiate with respect to x to get the E field in the x direction. Let me repeat that if you had a charge anywhere along this line and you stayed on the x-axis, the E field would be in the x direction. The magnitude would only depend on x. Here's the gradient of the potential. This is only a function of x. So when we take the gradient, we only differentiate with respect to x. So this will be the x component of E as a function of x. So putting in our v, we'll have minus k lambda, the minus sign comes from this one, times the derivative of log x over x minus l dx. And so taking that derivative, we get minus k lambda times l over x times l minus x. Realizing that x is greater than l, we can reverse that by putting the minus sign inside, and so we get k lambda times this quantity here where x is greater than l. So if you take the case where you have x much larger than l, then this would be a constant. L is a constant. This would be x squared down here, and so you'd have your 1 over x squared dependence, which is what you would have for a point charge. For x much larger than L, E falls as 1 over x squared, as it should, and it's not obvious. V goes as 1 over x at large x. What I mean by not obvious is you have to expand this. Well, let's do another version of this problem, and that is to put the point on the z-axis. And so we have our same charge distribution, same potential equation, and so we're going to start with the same equation for the potential. Now our r vector points along the z-axis, and so we write it as z hat. Our r vector is the same, r prime vector is the same, and our r minus r prime now is a z term and the old x prime term. So if we write our r minus r prime, we take this vector and find its magnitude, and that will be x prime squared plus z squared to the 1/2 power. So we have now this value for the distance. That's this distance right here from the dq. We put this here, lambda is a constant. We integrate along the x-axis here. So therefore the dx prime represents this element here. We have our k lambda out in front, and we have the integral of dx prime with 1 over this quantity right here. So if we look at the integral, here it is right here, the same integral that we just had. I used xx for x prime because x prime means to take the derivative of x. And I call this v perp because it's perpendicular to the line in the z direction. Let's plot it. Oh yeah, this is the integral. This is the answer. So you have log L plus and then the square root of this quantity over z. Because z can go to 0, we let this go to 0, so we plot this very close to 0. What we find, of course, is that it has the same type of behavior. It falls with the increasing z, has this little bit more complicated behavior as a function of z. That's the potential. If we look at this problem in terms of finding the E field, we are able to find the z component of the E field by taking the derivative with respect to z. That's okay, but you have to realize that there's an x component. So in other words, we really don't have the full potential as a function of x and z. There's a way to get that through a more general treatment. We'll be doing that in the near future. Okay, so let me just point out, if you have a dq here, it will have a vector like this, excuse the wiggle, and so therefore there's a E field that looks like this due to this dq. And you can see that it has both a z component and an x component. So that's what I mean when we say that the potential here is not as well defined to get the E field completely. So taking the derivative, here's the derivative with respect to z of our potential right here, and the answer is given right here. This is E sub z, component of E as a function of z.